In the previous videos, we defined the Fourier series of a piecewise continuous function, and we looked at some examples. But having a Fourier series of a function isn't helpful unless we know how it's related to the original function. So the point of the Fourier series is that you have some piecewise continuous function, you form the Fourier series, and then that should be related to your original function somehow. Because if your function wasn't related to the Fourier series, then there wouldn't be much of a point in defining the Fourier series. I mean, the point of the Fourier series is that it's supposed to help you analyze the original function f. So it turns out that in many cases, the Fourier series of f does converge to f. So here's a theorem. If f and its derivative are piecewise continuous, I'm sweeping a lot of things under the rug, but I'm just going to state the theorem and then explain it a little bit. On the interval from negative t to t, the Fourier series of f converges to f whenever f is continuous at x and converges to the average of the left and right hand limits at points where f is discontinuous. So let me explain this a little bit. So f needs to be a piecewise continuous function on this closed interval from negative t to t. In these videos and in the book that I'm following, they only define Fourier series when your function is piecewise continuous. Now, there are other functions that have Fourier series, but that's far too technical. So whenever we're talking about Fourier series, we're always assuming that your function is piecewise continuous anyway. And the derivative in the theorem, the derivative of f also should be piecewise continuous. And here we're assuming that f is differentiable. So if you have a continuous function, right, there might be points where it's not differentiable. But we're saying that where it is differentiable, the derivative is a piecewise continuous function. Okay. So if you have that, then the Fourier series of f converges to f whenever f is continuous. So at the points where the function is continuous, f of x is the Fourier series. Okay. The only place where f of x is not equal to the Fourier series is when your function isn't continuous. And when the function isn't continuous, the Fourier series, if you plug in a point where the function is not continuous, okay, into the Fourier series, then you end up getting the average of the left and right hand limits of the function. So let's look at a quick example to illustrate what this is saying. So let's say that f of x is this piecewise function which is -1 when x is between negative pi and 0, and 1 when x is between 0 and pi. So what this function looks like is, here's -1, here's 1, no, negative pi, and then this function is negative 1 from negative pi to 0, and it's 1 from 0 to pi, like this. Okay? So that's your function f of x. And the question is, what is the Fourier series of f converge to? So the Fourier series is an infinite series, right? So we're saying, you know, when you have an infinite series of functions, which is what the Fourier series is, when we're saying what does the Fourier series converge to, we're talking about the limit of that series, right? We're looking at the limit of those partial sums. Okay. Well, the theorem says that we have to look at where the function is continuous. So where is this function continuous? Well, this function is continuous everywhere. So f is continuous on the interval from negative pi to pi, except for 0, because the function isn't defined at 0 and there's a jump discontinuity, right? So by the theorem, the Fourier series converges to f of x at points of continuity. So it's going to be equal to f of x at points of continuity. So from negative pi to 0, the Fourier series is going to converge to f of x. So it's just going to be negative 1 from negative pi to 0, and it's going to be 1 from 0 to pi. Okay. But where the function is not continuous, so that's in this example at x equals 0, it's going to converge to the average of the left and right hand limits. Well, if you look at what's going on here, the right hand limit is 1, the left hand limit is negative 1, right? Because this function, the values are negative 1 when you go to 0 from the left, and the values are 1 as you approach 0 from the right. So, okay, so the limit of the function as x goes to 0 from the right is 1. The limit as x goes to 0 from the left is negative 1. And so when you take the average, and you add them, you divide by 2, you get 0. So the Fourier series converges to 0 at x equals 0. Also, the Fourier series is periodic with period 2t. So the Fourier series is going to go on forever. So the original function f here was only defined from negative pi to pi, but the Fourier series is going to be periodic, and so it's going to repeat forever. So it's going to go from pi to 2 pi like this, and then from 2 pi to 3 pi it's going to be like this, and it just keeps going on forever, right? You just take this and then shift it over to the right and to the left forever, and that's your Fourier series. That's what the Fourier series will look like if you were to graph it. Yeah, and then at pi, okay, so here's something I'm sort of sweeping under the rug. So my function, if you want to look at, let's see. If you want to continue the Fourier series, you should look at the extension of f of x forever. So you should take the Fourier series, you take the function f, and then you shift it to the right forever. So you look at the periodic extension like this. Okay. And then when you look at the periodic extension, then this Fourier series, then you can apply the theorem to this function f of x. And then the Fourier series will also be periodic like this. So in this case, and it just goes on forever. This case, the Fourier series almost looks like the original function. The only difference is that the Fourier series is defined at multiples of pi, and the value at pi is 0. Okay, so in this video, we explored conditions when the Fourier series of a function converges to the original function. This isn't the only time when this happens. The theorem says that if f and f prime are piecewise continuous, then the Fourier series converges to f when f is continuous. But there might be other functions where the Fourier series converges to f. So if the Fourier series converges to f, I'm not saying that f and f prime have to be piecewise continuous. But if they are, then the Fourier series does converge to f at points where the function is continuous.